Okay. Well, we are wrapping up our section on infinite series. More precisely, infinite series of numbers, or numerical infinite series. And then today we get to start our infinite series of functions. So we get to make it more complicated in 10 minutes. All right? Nice and scary for the season. So let's go ahead and look at the last two examples in this section. And what we saw on Tuesday was that the ratio test is really good if you see a factorial, and the root test is really good if you see a power on the outside. So let's go ahead and try those two tests for these two examples. So as soon as we see that factorial, that's probably the most definitive indication that the ratio test is going to be the best test, if you see a factorial. And so the root test, generally they use the letter R in this book. They always use the letter R to represent the limit of the ratio of consecutive terms. So we're going to look at the ratio of consecutive terms. So we're going to look at a sub k plus 1 over a sub k. So this is called the ratio of consecutive terms. And we take the absolute value. And the reason we want to use the ratio test with this factorial summand is that when you use the ratio test, you're going to get to cancel all the factorial symbols. So that's why the ratio test is such a good test when you have these factorials. So when we figure out what a sub k plus 1 is, we come over here and we replace all the k's with k plus 1. So this is going to be k plus 1 factorial. And then all of that is raised to the third. So that's the numerator. K plus 1 replaces the k. And then in the denominator, we replace that k with k plus 1. So we have 3 multiplied by k plus 1. And then all of that is factorialed. And now we're going to divide by a sub k, which is the same thing as multiplying by the reciprocal of a sub k, which means we just flip this. So dividing by a sub k is multiplication by the reciprocal. And that's going to give us 3k quantity factorial divided by k factorial quantity cubed. And there's no absolute values anymore. All of this stuff is positive. So we don't have to worry about the absolute values. So we can take them away. All right, so let's carefully expand everything that we can expand and then cancel what we can cancel. So up here, we have k plus 1 factorial. And we know that k plus 1 factorial is k plus 1 multiplied by k factorial. And then all of this is cubed. So there's going to be a cube on top of that. And then there's going to be a cube on top of this k factorial part. So we take k plus 1 factorial, we break it into two parts, k plus 1 times k factorial, and then we distribute that exponent down to both factors. Down here, this becomes 3k plus 3 factorial. Down there, we distribute the 3. Over here, we're going to bide our time. We're not doing anything over here. This is coming from a sub k. We're just going to leave these as is and hope that we get some cancellation. Well, right off the bat, we see, ooh la la. K factorial cubed, those go away. Those cancel each other out. They divide into each other, give 1. Okay, so let's try to expand this factor down in the denominator and see if we can get some cancellation with the numerator. So let's remember what the factorial symbol tells us. So the factorial symbol tells us that we're going to take whatever's in the parentheses and then subtract 1, and then subtract 1, and then subtract 1, and then subtract 1, all the way down to 3, 2, 1. So let's start doing that. So the numerator, there's not a lot we can do. We don't want to expand this k plus 1 cubed. That would be kind of a pain, so we're going to just leave this alone. So down in the denominator, 3k plus 3. So we're going to expand this out, so that's 3k plus 3. What would the next factor be in this expansion?
3k plus 2.
3k? Yeah, 3k plus 2. And so we have a choice where we put the factorial symbol. Right? If you have, say, 5 factorial, you could write this as 5 times 4 factorial, if you want. Or you can keep going in your expansion. You could write this as 5 times 4 times 3 factorial. Right? You can drop the factorial in wherever it's convenient. You're going to put that factorial symbol in. And so what we're going to do, what we're seeing is that we're targeting this 3k quantity factorial in the numerator, so we want to keep going. So the next factor here is going to be 3k plus 1. And if we wanted to put the factorial symbol there, we could. Or we can subtract 1 another time, and we'll get 3k. And let's put the factorial symbol on that 3k, because that's going to give us cancellation with the numerator. So we do repeated subtraction of 1 until it's convenient to stop. Now it's convenient to stop because we've got that common factor that we can wipe out. And this is why the ratio test is so good for factorials, because you can always get rid of the factorial symbol with this ratio of terms here. All right, so now this limit is as k goes to infinity. And what we have in the numerator is a cubic. You can imagine multiplying it all out, right? You get k cubed plus blah, 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 plus 1 at the end. That's a cubic. The denominator is also a cubic. If you were to FOIL this all out, you would get a cubic polynomial, a power of 3. Everyone agree? And when you start FOILing here, the leading term is going to give you the dominant term. It's going to give you that highest power of k. Now, when we take a limit at infinity, which we're doing, a limit at infinity, and you have polynomial over polynomial, everything depends on the dominant term in the numerator and the denominator. If you have the limit as k goes to infinity of, say, x, let's do the k, since I put a k there. So if we have k cubed plus 2k squared plus k minus 10 over k cubed plus 2k plus 1, what is the limit of that?
1.
All you have to do is look at the leading terms here. All of these are insignificant when you take a limit at infinity. You only need to look at the leading terms. And we've learned that because the math behind it would be divide everything by k cubed. And if you divide everything by k cubed, all of these little fractions will go to 0. And so we can, without any loss, we could say, hey, that's going to be an expanded cubic, and the leading term is k cubed. This is going to be a cubic if you expand it. We don't care about the littler terms. We just care about the dominant term. 3 times 3 times 3 is 27k cubed. So if we look at the dominant term of the numerator and the dominant term of the denominator, that's going to be enough. And then the k cubes cancel, and we get a limit of 1/27. All right. So questions before we draw a conclusion based on the value of that limit?
On this problem, I know that we're dealing with factorials, but is factorial cube growing faster than 3 times k factorial, or is it the opposite?
So both are going to infinity.
Mm-hmm.
And when we take this limit, that's what we're concluding. This is what's going to, let's talk about the conclusion in 1 second.
Yeah.
Does everyone understand the mechanics of the cancellation and all that stuff and the evaluation of the limit? So, the next question is, what does this mean? So the 1/27th, what does the ratio test tell us? If this value is less than 1, what happens?
Converges.
Converges. Just like the geometric series. Do not forget, geometric series is so vital. You have to have this in your mind down pat. If the absolute value of r is less than 1, you have convergence. Or it implies convergence. So if absolute value of r is less than 1, converge. Same for the ratio or the root test. If you get this limit, r, same type of thing, this is less than 1, that tells us that we have convergence. Technically, it's absolute convergence since we took absolute values, but because everything's positive, absolute convergence is redundant, doesn't matter. It's the same as regular convergence since there's no negatives. So, you tell me now, if this series converges, is the top or the bottom going to infinity faster?
The bottom.
The bottom. Because the only way a series can converge is if the terms are going to 0.
Slower than the bottom.
So the only way they can go to 0 and get convergence is if the bottom is going to infinity faster than the numerator. Significantly faster. Because they have to go to 0 and they have to go to 0 pretty fast. And so the denominator is growing faster than the numerator. So 3k quantity factorial is growing faster than k factorial cubed. Okay. Let's look at this one. Now, one thing we've seen when we've looked at this type of thing is that it almost looks like an E thing, almost. But remember, the E thing, the outer power is just k, not k squared. That E thing, remember the E thing says that if we have 1 plus a over k to the bk, that goes to e to the ab as k goes to infinity. So it's almost an E thing, but it's not, because the outer power is k squared, not just k. So it's not an E thing, but it's close. But when we take the kth root here, let's use the root test. So the root test, they use rho for the root test, just to distinguish it from r for the ratio test. Greek letter r, really. And we take the limit as k goes to infinity of the kth root of the absolute value of a sub k. So the root test says we're going to do that. And when we take the kth root here,
You're against the square.
so we're going to take away one of the k's from that exponent. All right, we take the kth root. Now, we have an absolute value bar here. We need to make sure that this expression is always positive. If it's not always positive, we have to make a manipulation. Is this always positive down here? So k starting at 1, or at least is it never negative? If we plug in k equals 1, we get 0. K equals 2, we get 1 minus a half, and then 1 minus a third, 1 minus a fourth. So it's always positive, other than the first term is 0. So it's always non-negative. Always non-negative. So that's good. And now this is as k goes to infinity. And what is that? Come on, you can do it. What is that equal to?
E.
What kind of E?
E to the first.
E to the
1 over
negative first.
Oh, yeah.
Because we think about moving this negative into there. Because our form here says plus. So if there's a minus here, we push it into the numerator there. And then the a is -1 and the b is +1. So this is e to the -1, 1 over e. And now we do our analysis. Root test, ratio test, same as geometric series. If you have the limit being less than 1, is that less than 1? 1 over e, 1 over 2.7, right? It's less than 1, about a third. This is less than 1, same conclusion. We have convergence. Technically, we have absolute convergence, but there's no negatives in here, so it doesn't matter. Convergence, absolute convergence are the same if there are no negatives. So we have converge. Now, if this was a positive one here, and you got your limit to be e and not 1 over e, what would the conclusion be?
Diverge.
We would diverge. So converge, less than 1 for the ratio, the root, or geometric series. Greater than 1, diverge. So that would be very different if that was a plus right there. Then it would diverge. So let's take a peek at 10.8. This summarizes kind of the way you should attack a series. 90% of the time, it's important to think about the divergence test, because we've learned that the only way you can add an infinite collection of positive numbers together is if they have to go to 0 in the tail. If they don't go to 0, the sum is going to go to infinity. So we know if the terms don't go to 0, the series diverges. So we think about that first. Maybe we don't write it down, but we at least think about it. If it's not 0, diverges. And then we've got these special series. Geometric series. So those are these things that look like a r to the k. The exponent is where the k is living. That's exponential. That's called a geometric series. So geometric series, k is up there. If r is less than 1 in magnitude, we get convergence. Telescoping series, you have that subtraction thing, and you find s sub n and take the limit of it. P series, so let me just write down the geometric series is the one that, so geometric series, you usually see the standard form as a r to the k. And then the P series is the one that it's very easy to confuse it with. Here the k is in the denominator, and the P is the power on that k. So here you're in the numerator, r less than 1, you have convergence. Here you're in the denominator, p greater than 1 gives convergence. So these are the two that are very easy to mix up. Don't do it. Alternating series, if you see a switch, -1 to the k, -1 to the k plus 1, alternating series, go with the alternating series test. If none of those are working, if you come through, you divergence test, geometric, it's not special. So special means it's got like a particular name to it, geometric, telescoping, P, or alternating. Then you look at the summand. What's inside the summation symbol? Is it integrable? Maybe we should say easily integrable. If it's easily integrable, integral test is the way to go. Factorials, ratio, always. Powers of k, root. And then the one other pair of series or pair of tests are the comparison tests. And so if none of these are working, then a lot of times you can compare. And so when you're thinking about a comparison test, you're taking away insignificant pieces of the summand. You only want to go with the comparison test if when you take away the insignificant pieces, you get to something that looks like a p-series or looks like a geometric series. It's got to be something that you know how to handle easily. These two, we say, can be handled easily. And if R is less than 1, it converges. If P is greater than 1, it converges. Like, that's about as simple as it gets when you're analyzing a series. So when you're going comparison, you're trying to compare it to something that you can analyze very easily, looking at it as a P or a geometric series. A P or a G. So here we go, random series. So we look at these things. Now, when you think about the divergence test here, maybe it's easier if you don't like negative exponents, which most of us, maybe we don't not like them, but maybe we don't love them, because it's always harder to analyze when you have negative exponents. It just is. And so it's possible to rewrite this without negative exponents. So that's one thing to think about. So if when you look at that and you're not sure what the limit of it is, get rid of the negative exponent. Then it's easier to evaluate the limit. Now in your mind, if you leave the negative, hopefully you're seeing that as an exponential function that's decaying because the exponent is always negative. But you could get rid of it. So let's get rid of that negative exponent. And the way I'm going to do it is strategically. Because I know that having a k up in the outside is good, right? That could be a geometric series. Or it could be something that we apply the root test to. So having a k up there is okay. So what we're going to do is implement that negative 2 onto the 7. So we're going to treat this as a power raised to a power. 7 to the negative 2 raised to the k. 7 to the negative 2 is 1 over 49. And we'll use our shorthand notation here. We know it's an infinite series. We've already established that. If we just put a 1 there, we know it means k goes from 1 to infinity. So that's a special series. That is geometric. Right? It's a r to the k. Now, we just have to identify. So the way I know you know it's geometric, if you don't just say it's geometric, you have to identify the two pieces of a geometric series, a and r. What is a for this geometric series?
1.
Over.
Oh, 1 over 49. I thought that was R.
It's also r. So remember that a is the very first term in the series. If this started at 0, then the first term would be 1. But because this starts at 1, the first term, you plug in the k value of 1, and we see we get 149. If this series started at 2, then a would be 1 divided by 49 quantity squared. So a is always the very first term in the series. We find the first term in the series by plugging in the initial k value. Now the r value is usually the one that takes less brain power because it's whatever's below the k. It's whatever the k is on. It's whatever's in the parentheses. So that one is also 149. So there is those are our two pieces for a geometric series, a and r. And we know that the sum of a geometric series is a divided by 1 minus r. So for us, with this particular series, we have 1 divided by 49 over 1 minus 1 divided by 49. If you multiply top and bottom by 49, you'll end up with this. So we get 1 over 48. So that is the sum of the series. Geometric? Yeah, Joey?
I have a question. So for the A, so if it was 2 right there, then you would plug in 2 to the K?
Yes, exactly. So if that started at 2, to get the initial term in the series, we would take a 2 and plug it up there, and then we'd evaluate that. Yep.
Is doing the root test okay?
Say that again?
Is doing the root test okay? Because I got the same answer.
Of course. So here's the difference.
Well, I didn't get the same answer.
Yes, exactly.
Got it.
So the root test, right? If you use the root test here, you take the kth root of this, you get 149. That's bigger than 0, so it converges. Excuse me.
Smaller than
it's
1.
smaller than 1, so it converges. But it doesn't tell you what it converges to. So the only two series that we can actually know the sum of are geometric and telescoping. So we'd want to use the test that gives us the most information. So if we have a geometric series, yes, the root test would show that it converges because the kth root of this is less than 1, but it doesn't tell us what it converges to. So we prefer to use the geometric approach here because it actually tells us way more information. It tells us it converges, and it tells us what it converges to. So the sum of the series is 1 over 48. The series converges to 1 over 48. You can say it in lots of different ways. But yeah, we always want to go with the one that's most precise if possible. All right, so what test?
Ratio.
Ratio. As soon as we see the factorial, that is a indication, jump straight to the ratio test. So the ratio test says limit as k goes to infinity, absolute value of a sub k plus 1 over a sub k. So our subscripts are k plus 1 and k. So we're looking at the ratio of consecutive terms. So we need to be a little careful here. First, we're going to do the a subscript k plus 1, a sub k plus 1. So we put a k plus 1 in for the k. That's going to be 4k plus 4. Everyone agree? So if you replace that k with k plus 1, the 4 has to distribute. So you're going to get 4k plus 4. So let me not, I'll do it in 2 pieces just to make sure you're seeing that. So there's the a sub k plus 1's numerator. We will get 4k plus 4 in a moment. Down below, we have k plus 1 replaced in for the k, so k plus 1 factorial, and all that's raised to the 4th power. So there's our a sub k plus 1. Now we're going to divide by a sub k, which means multiply by its reciprocal. So this will give us k factorial, quantity to the 4th power, divided by the quantity 4k factorial. So let's go ahead and do some expansion here. So we can, obviously we want cancellation. So in the numerator, that's going to be 4k plus 4 quantity factorial multiplied by k factorial raised to the 4th power. Down below, we've got the 4k quantity factorial. That's not going to change. But here, we know that k plus 1 factorial is k plus 1 times k factorial. We have k plus 1 multiplied by k factorial. Both of those are raised to the 4th power, so we distribute that 4th power onto each of those factors. And then we have the 4k quantity factorial. So that's our first expansion step. And right away we see that the 4k, or excuse me, the k factorial quantity to the 4th, those are going to cancel. Those are going to cancel. And then we see that, ooh, there's going to be some cancellation with the 2 factorial pieces here if we can do some expansion of that numerator. So let's see, when we expand that numerator, can we get a cancellation? Of course we can. So that's going to be 4k plus 4 multiplied by, so now we're going to do our repeated subtraction of 1. 4k plus 3.
4K.
Yeah, we're going to keep on going, right? You can see it now. So we're just going to keep subtracting 1 until we get to a very convenient stopping place. And that very convenient stopping place is right now.
Well, one more. And then a
The
factorial.
factorial, yeah, well, yeah, exactly, yes. Yeah, that's 100%, right there.
Ooh.
All right. So now down below we have the k plus 1 to the 4th. We have the 4k quantity factorial. And now You see that we can cancel those. Those are gone. And we're in a really nice position here because the numerator is a polynomial. The denominator is a polynomial. Polynomials are the easiest thing to take limits of. The only term that matters in both the numerator and denominator is the dominant term, which is the term with the highest power of k. So we don't have to FOIL this all out. All we have to do is grab the highest power of k for each of those, and that's what's going to generate the leading term if you were to expand it all. 4 times 4 is 16. 16 times 16 is 256. So we are going to have 256 k to the 4th. That's the dominant term in the top. In the bottom, same thing. If you multiplied that all out, the dominant term would just be that k to the 4th. Those k to the 4th cancel. We get 256. And what does that tell us?
Divergence.
So this is greater than 1. So make sure you compare it to 1. With the root or the ratio or the geometric series, you compare to 1.
Yep.
So make sure you put that in there. That's greater than 1, therefore it diverges. So therefore diverge.
Since it's so much bigger than 1, does that mean it diverges really quickly? Or
That's a good question. I would
so?
be inclined to say that the larger that is, the faster it's sort of rising towards infinity.
Because that's how much bigger it is than the
Then,
denominator. So.
yeah. I think that's a fair assessment. It definitely tells us that the numerator is going to infinity faster than the denominator. And if this number were smaller, I would say that this one goes faster. They separate faster. Yeah. So, geometric series, ratio test. You want to be able to recognize those geometric series instantly because those are pretty fast. Let's take a look at the next series. Okay. What test jumps to mind with the second one?
That's the E1.
It is an E1.
What is T?
So when we think about the divergence test here, we would think, oh, that's in the form. We could probably try to rewrite this so that this might be in this form. But notice one difference. Is there a k in the base here?
No.
There's no k in the base. The k is only in the exponent, so it's not actually in this form. It looks similar to it, but because there's no k, this is just a constant to the kth power. And what is a constant to the kth power? Constant to the kth power is geometric. So the only question we have here, I guess we might as well finish this one since we were talking about it. It's geometric. So if it's geometric, you have to identify two things. You have to identify R and A. And what is A going to be in this case?
E plus 1 to the power of pi, or divided by pi.
Exactly. E plus 1 divided by pi. So we put in the k for the power. K is 1. So that is A. How about R?
Same thing.
Same exact thing, because this started at 1. If it started at 0, then A would be
1.
just 1. If it started at 0, we would raise this quantity to the 0 power and get 1. So now we have to look at the common ratio here. Geometric series, converge, diverge, all based on that R value. Is it bigger than 1 or is it less than 1?
Bigger than 1.
E is about 2.7, and if you add 1, you get 3.7. 3.7 is bigger than 3.1, so this is bigger than 1. Bigger than 1, which tells us diverge. Now, think about using the root test here also. The root test, if we took the kth root of this, the kth root of this gives us the same constant. It's bigger than 1, so we have the same conclusion. Because the root test and the geometric series, same condition. Bigger than 1 diverge, less than 1 converge. Okay, so you could do this This one, you could do either way, and it doesn't matter because you have divergence. When you have a geometric series that converges, you really want to use the S equals A over 1 minus R because you can tell what it converges to. All right, now this one is a little bit incognito. It's bad when we don't have just a singleton K in the exponent position. So this is bad because we've got this extra stuff happening in the exponent position. But we know algebra. We know how to modify this. So if you have an exponent that has a K that has something added or subtracted to it, just use the laws of exponents. We can write this as 3 to the K multiplied by 3 to the 4. 3 to the 4 is just a constant. And we know constants do not affect convergence or divergence. You can just factor them out. If you have a convergent series, those constants will affect what it converges to, but it doesn't change divergence or convergence. And this is going to be 5 to the K multiplied by 5 to the negative 2. All right, so we've now whittled the exponents so that you have just K's for these two factors. The constants, again, are meaningless in terms of converge or diverge, so let's just move them to the front. So we're going to move them out. So this is in the numerator. 3 to the 4 is 81. 5 to the negative 2 is actually 5 to the positive 2 up top, so it's 25 in the numerator. So out in front, we're going to have that as our constant. And then inside, we have 3 to the K and 5 to the K.
3/5.
We're going to make it 3/5 to the K. We want one single K. If we can whittle it all the way down to 1 K on the outside like that, that's best. Best case scenario. Okay. What kind of series is that?
Geometric.
Geometric. We have this arc form. R to the K is geometric. As soon as it's geometric, you identify A and R. So what is A for this series?
1.
Everyone agree? That initial index value is 0. We put a 0 in the exponent position. So we're looking just at the series part here. We've got the constant in front, but we're looking there. So A is 1. R is whatever's below the K, so that's 3/5. Now we can tell that this series, this is less than 1, so we know it's going to converge. Geometric series, root test, ratio test, less than 1 converge, greater than 1 diverge. So, the sum of the series is going to be A over 1 minus R, but then we also have this 81 times 25 out in front. So our total sum is going to have that amount out in front multiplied by A over 1 minus the common ratio. So that is going to be the total sum here. So here we have a geometric series. We know it converges, but if it's geometric, we can ask and answer the extended question, well, what does it converge to? And so this is going to be 81 times 25. Here, 5/5 minus 3/5 is 2/5, and if we flip it, we get 5/2. And then we would type that into our calculator, and we would get something divided by 2. 3,025 times 10,125?
Yeah.
What is it?
I just did it all out to a specific decimal number. So
Yeah, we
it's
don't
just-
want a decimal though. We want an exact form. So what's that numerator? 81 times 25.
10,125.
Once again?
10,100.
Oh, I might have even said that. Okay. So that is the sum of our series. Oh boy. I don't think we get tricky. So that is the sum of that geometric series. So geometric, one of the most important ones to recognize right away. Any questions on any piece of that? Finding A, finding R. Why is geometric? So a couple things that we noticed here, some principles. If k is not the exponent, if it's k plus or minus something, use your laws of exponents to whittle away the exponents so that you end up with just a k. And then if you have a power of k in more than one place, if possible, if it's geometric, you can always turn it into a constant raised to a single k and not have different places where you have powers of k. Let's look at these two, or at least this one. Oh, there we go too. All right, so with that top one, when you look at that, how about divergence test? Is the divergence test conclusive or inconclusive? In other words, what is the limit of this as k goes to infinity? 0? We agree? The numerator is a bounded function. What's the least the numerator ever is? 4. Because sine could be -1,
Oh, yeah.
right? Sine is a wobbler.
Right.
So it could be -1, and the most sine could ever be is 1. So the numerator is always just some number between 4 and 6. So it's oscillating around something between 4 and 6. But the denominator is an arc function, right? It's looking like a bird wing. It's going to infinity. So the denominator is going to infinity. The numerator is essentially constant, so the limit is 0. So the divergence test is
Inconclusive.
inconclusive. So if this limit is 0, we have to do more work. Just because the terms go to 0 doesn't mean it converges. They have to go to 0, and they have to go to 0 fast. And so the divergence test can only find egregious divergence, which means the limit is not 0. If the limit is not 0, it diverges. The limit here is 0, so it might converge, might diverge. Let's take a deeper look. So, when we look at this, when we think about the numerator being constant, and we think about this sign that's adding or subtracting from the 5, we have just sort of alluded to the fact that it's kind of insignificant. The numerator is just basically a constant. So what we're going to think about doing is comparing this to a p series that has a k to the 1/2 in the denominator. Okay, so the p series always has a power on the k in the denominator, and so this looks a little bit like a p series other than this sign of k thing. So let's go with comparison test. And here's where we have multiple choices. So in the numerator, you could say that the sign is insignificant and you can compare this to 5 over root of k. That's probably what most of us would say, okay, the sign is wobbling between -1 and 1, let's just get rid of it and let's compare it to this. Okay. Is that okay? You could also say sine's biggest value is 6, so maybe you put a 6 in the numerator instead of a 5. Or you might say, hey, sine's smallest value is 4, maybe you put a 4 in the numerator. Doesn't matter. No matter what constant you plug in here, this series that you generate is going to do what? Go down here. What's going to happen to this series regardless of what you put as the numerator?
It's going to diverge.
Right? This is a p series with p. How do I know you know it's a p series? You say, oh, you identify p, you compare it to 1, and you make a conclusion. And if p is less than 1, you have divergence. So the opposite of the geometric series. For geometric series, less than 1 is converge. For a p series, less than 1 is diverge. Sebastian?
So the p series can be included in other tests to kind of tell you if it is going to be diverging or converging, if it is in the right form.
Compare. So the only time we do this is when we're doing the comparison test.
Okay.
So the comparison test is where we look at something if it's P series-ish, if it's geometric series-ish, and we can compare. Using a non-P or a non-G for comparison is a pain because P series and geometric series, you can tell instantly whether they converge or diverge based on the P or the R.
Right.
So when we're doing when we look here, this is almost a P series. If this was just a constant, it's a P series. So that tells us that comparison is a good way to go because it's P series-ish. It's almost a P series. The numerator is essentially a constant.
Right.
So now we know that this thing diverges. If this was a 5 or a 10 or a 2, it would still diverge.
Right.
And so here's where we might want to modify what we choose as that numerator. We know that we want to show that a sub k, the a sub k is right here. This is what we're analyzing. This is our a sub k. The b sub k is the one that we chose. We chose b sub k that diverges. So do we want to show that the a sub k's are bigger or less than the b sub k's?
Bigger.
Less. All right.
So did the b sub k's diverge or converge?
Diverge.
They diverge. Is smaller than diverging conclusive? If you have a series that diverges, something that's less than it could also diverge, but it could also converge. So bigger than diverging will diverge. Smaller than converging will converge. So we would like to show that the A's are bigger than the B's. If the A's are bigger than the B's, bless you, then the A series also diverges. So that's what we want to show. So let's take a look. So we're going to take the a sub k, 5 plus sinc over square root of k. We don't know, so we put a question mark right there. We're not sure, is that? So we get that. Now you can multiply both sides by the square root of k, and those just cancel. Right? Those cancel if you multiply. And now, is that inequality, like just think ahead here, is that inequality going to be true or false?
Not always true.
Right, so false. So it's going to be false. So for an inequality to be true, it has to be true for all replacements of the variable. And so it would be true sometimes and not true others. But what is the issue? So let's just come over
Sign is
here.
oscillating.
So we can subtract off the 5s, and we're going to get sinc, sine of k. We're going to get, is that greater than 0? Right, and that's not true. That looks like a 5. Yes. So
It's not always true.
So that is not always true. All right, so that's false. But the only issue was this right here, was this constant. If we come back here and say, wait a minute, let's just choose a bigger constant. Let's choose whatever number you want that's, say, bigger than 6. Let's pick 10, just for the heck of it. So if we pick 10 here, now another option is just to go to the limit comparison test instantly. Of course you could do that. But let's just notice, if we say, hey, let's pick a bound for this numerator. 10 is a bound, 11 is a bound, 6 is a bound. You can pick any number. So if we pick 10, we still have divergence here. Still have divergence. But over here, and the a sub k doesn't change. So if we change this to a 10, does that make the inequality true?
Yes. Change it by 10. Yes.
Sure? So if we subtract 5, we would get sine of k bigger than 5.
Oh.
That's still not true. Everybody agree?
Oh, yeah.
So
Sorry.
let's try the other way. So what if we pick the lower bound? So what if we say, hey, well, it doesn't matter what this constant is. Let's pick a smaller number. Let's just pick 1. So if we pick 1, 1's easy. It still diverges here. That still diverges. But now we come over here and we say, okay, now that 5's no longer there because we chose 1 over root of k. Now is it true?
Yes.
So we have, let's do this inequality all the way out just to make sure you're seeing it. So we have 5 plus sine of k. Is this greater than or equal to 1? We subtract off the 5, and we get -4. Sine is always greater than or equal to -1, so this is true. So now we've picked a constant that gives us the direct comparison test as a definitive test to use. So therefore, both diverge. So this one diverges. This one must also diverge. So sometimes with the comparison test, you can fiddle with it and make the inequality give you what you want it to give you. Not always. And if it doesn't, you could instantly go to the limit comparison test if you don't want to sort of fiddle with it. But fiddling with this constant sometimes makes it pretty easy to make it do what you want it to do. And usually what you're going to do is pick a number that's bigger than the numerator or smaller than the numerator. So, all right, let's try this one. Same idea here. This looks very p-series-ish. This is essentially a constant. It's wobbling around between 2 and 4. Right? Cosine's a function that goes between -1 and 1. So the numerator is going to wobble between 2 and 4. One above the 3 or one below the 3. Right? It's going to add or subtract a little bit from the 3. So between 2 and 4. So it's like a constant.
How do you know that's going to wobble between 2 and 4?
You tell me. What does cosine do? When you visualize cosine in your head, what do you see? Do you see a wave?
Yeah.
And that's what you should see. You should see a wave. When you visualize sine or cosine, this is what you should be seeing.
Right.
Right? And cosine, no matter what the angle is, cosine's always capping out at 1 and dipping down to -1 and up to +1 and down to -1. Right? There's no coefficient outside of the cosine. So cosine, doesn't matter what the angle is. Cosine of 5 million k, cosine of 10 million divided by 5 factorial times, it doesn't matter. Anything that's in the angle, all that adjusts is your period. Or possibly a shift. But it's not addressing the amplitude. So the inside, no matter what it is, if you have a 1 on the outside, all you should be visualizing, no matter what or how crazy the inside looks, it's going up, capping at 1, dipping to -1. It's never more than 1, never less than -1. So you should be imagining this very gentle wave forever. And so if you add a constant to that, that's just going to shift it up. So this is at most 1, so the numerator is at most 4. This is at least -1, so the numerator is the smallest the numerator ever is 2. So when this is the most negative it could be is -1, so the numerator would be 2. So the numerator is going to go between 2 and 4.
Oh, okay, yeah.
Make sense?
Yeah.
And the denominator is going to infinity, so we know that the divergence test is inconclusive. The limit of this whole thing is going to be 0. But let's do the comparison thing again. So once again, when you choose your b sub k, so last time we were like, oh man, we probably should have just picked 1 over root k to start with. Let's do that this time. Let's just say, hey, let's just start with this. Let's just go with 1, just for the heck of it. Doesn't matter what the numerator is. Does not matter. So this series that we generate, how do I know that you know it's a p-series? You identify p. You compare it to 1. That's bigger than 1, so this p-series converges. So now the comparison test says, let's compare the a's to the b's. So we've got the a sub k, which is the original. A sub k is the one that we are analyzing right there. That's a sub k. The b sub k that we selected converges. So the a sub k series will converge if it is smaller than the b sub k series. Smaller than b sub k, smaller than converging will converge. So that's what we would like to show. If we can show that this is true, we're done. then it converges. They both converge. So we look at this a sub k thing, and now we're gonna be like, oh man, did we pick the right numerator? We don't know. We have 1 over k cubed. Once again, we can cancel the k cubes here, or cancel the denominators, multiply both sides. Is that thing less than 1?
No.
No. So then we go back over here and we're like, oh man. But we could go to limit comparison test, or we could say, oh man, let's just change the numerator. What do you want to change that numerator to?
10.
10. Let's go with 10. Put a 10 there. This still converges. Doesn't change anything. But now this is a 10, and now it's going to be true. So as long as you pick something, and I put a strict less than here, so as long as we pick something that was 5 or more. Chewy?
I have a question. For the A and K, how come you can change it to whatever you want?
So when we pick our b sub k, normally the process is to erase anything that's insignificant. So things that aren't dramatic. So down here we have a k cubed, which is that's dominating this expression. So the 3 is a constant, so we would say it's insignificant. So we can get rid of that constant because it's insignificant. This is also like a constant when k gets very large. This is like a constant. And so we can take the part in yellow, the numerator, and replace it with any constant that we want. And so if we pick a 1, we would get convergence. If we pick a 10, we get convergence. If we pick 100, we get convergence. So it doesn't matter which constant we get. But a lot of times when you're using the direct comparison, whatever constant you pick matters when you're trying to compare. Now you could, if you didn't pick the right constant, you could of course go to limit comparison test. But in this case, we can actually do a little bit of finagling and change that constant. And we see here that when we change the constant, so now we're going to subtract 3 from both sides. And that's always true, right? Cosine is always between -1 and 1. That's always less than 7. So this is true no matter what. So therefore, both series do the same thing. We chose a comparison series that converged. That means this series also converges. So therefore, both series are going to converge. And so that b sub k, you can pick anything you want. You can pick 1 over k squared, 1 over k to the 4th, but 99% of the time you're not going to be able to show. You usually want to pick your b sub k carefully, by taking away the insignificant pieces. But you can pick anything. If you can show that it's always less than something you know converges, then it's going to converge.
Now, would there be any problems in which the first part would say converge and the second would diverge? Or would they both have to be the same, like both diverge?
Wouldn't be able to prove
Yeah,
it.
they always have to do the same thing.
Right.
So if you can show that this inequality is true, then they always do the same thing.
So like the last problem, how it didn't make sense originally,
Yep.
because you chose a different constant. You just need to choose a constant to make it true.
And as soon as we choose a constant that makes it true, then this is definitive. If you have a true statement here, then the original series is going to do whatever your comparison series does.
Okay.
So they always are going to both do the same thing if you can show this to be true, whether it's bigger than diverging or smaller than converging.
And when you're picking a new constant, if you're diverging, you want it to be a smaller number, and if you're converging, you want it to be a bigger number.
Yeah. That will always be the pattern.
Or just go to the limit comparison test.
Or go to the limit comparison test. Exactly. You can always just jump to the limit comparison test, which is not bad. Let's go ahead and take our 10-minute break, and then we'll come back. And both of these, what test do you think we're going to do first with both of those?
Geometric.
Oh, geometric. Interesting.
Let me.
I see root test,
Or root test.
because I see these powers here. We'll see. Maybe one of them's geometric. We'll see.
Well, root test is easier to me, but
Yeah, root test.
I figure you should always try the geometric.
If it's
that way you get
geometric, yeah. So think about whether,
we're already.
is it geometric?
Oh, not the top one. It's k plus 2. I thought it was 1 plus 2.
Yeah.
Which wouldn't make any sense. Yes.
Right, exactly. So it's not geometric, so we definitely are gonna go root.
The bottom one might be.
Let's see. So we have these two series to analyze. And when we look here, there is certainly a power of k that you could pop to the outside. So let's rewrite both of them with that in mind first, so we can rewrite them so that there's just a single power of k on the outside. So here we have k over k plus 2, all raised to the k. And here, if we did the same type of thing, we want to consolidate all these powers of k that we see. We would have that. So now that we have that power of k consolidated out there with just a k, not a 2k, not multiple k's, now we should be able to identify if either of them is geometric. Are either of those geometric? No, because for geometric we would need a constant raised to the k. And both of these are funny. There's a k in the base and there's a k in the exponent position. Right? There's in both places, which is sort of a modified power tower type of situation. All right, so both of these, you should be inclined to use the root test. Because we have this outside power of k, let's go with the root test and see what happens. So for this one, the root test, usually they use a row in this book. So we want to take the limit as k goes to infinity of the kth root of the absolute value of a sub k. The first thing we kind of notice is that it doesn't really matter that we put absolute value because everything is positive already. So we don't need the absolute value. So when we come down here and we take the kth root of this, the kth root of this quantity to the kth just takes away the power. So this is going to be limit as k goes to infinity of k over k plus 2. And what is that limit?
1.
1.
But what does it mean when that test equals 1?
And what does it mean?
It's not less than 1?
It's not less than 1, it's not greater than 1, so the test is inconclusive. Yeah. So that means we need to do something else. So this is the, oh shucks. This is inconclusive. So this is like the divergence test. You know, when you have a limit of 0, it's inconclusive. You have to do more work. Whenever you get an inconclusive, you have to do more work. And here's where it's going to get interesting. So when we look at this here, it looks a little bit like our E limit. Looks a little bit like it, right? Looks a little bit like our E limit. So let me just keep that up on the board. So if we have 1 plus A over K raised to the BK, we know that that goes to E to the AB. This looks a little bit like that, right? So let's do this. So let's check out this modification. So we are going to, I am going to first flip the base. But if I flip the base, what has to happen to the exponent? It becomes negative. Okay, fine. Now, in the base, the denominator is a single term, so you can split the fraction. You can split the fraction. You can make this 1 plus 2 divided by k all to the negative k. Now, it is in our E form over here. What is the limit of this as k goes to infinity? e to the what?
-2.
E to the -2.
Or
Or e squared.
1 over e squared. And what does that tell us?
It's less than one.
Say again?
It's less than what is?
So it's less than 1,
So it's gonna be
but all we've done is take the limit. We haven't applied a test. So we haven't done a root or a ratio or a geometric where we compare to 1.
Oh, that's G.
This is the
So they're-
divergence test.
So it's in. Oh no, it's greater than 0.
So the divergence test says if the limit of a sub k is not 0,
considered
then it diverges. Right? So that's what this is. So we took a sub k, we fiddled with a sub k, so this is essentially the divergence test. And we're getting a limit that's non-zero, so we know instantly that it diverges. Yeah, so this is where we can get a little tangled up. Many times we compare to 1. So we have to remember, geometric series, root test, ratio test, those are the 3 that we're comparing to 1. For the divergence test, we're comparing to 0. The divergence test says if the limit is not 0, you're adding, in the tail, 1 over e squared to itself forever, which is going to diverge. If you add any positive number to itself an infinite number of times, you have divergence.
Can you increase the dots in the therefore? It looks so small that I can't see it.
I can do that.
Because otherwise, if I was see it, I'm just like, what is that?
What is that?
Drive me crazy.
Yeah, totally fine. So that is divergence. And we've seen that root tests can be inconclusive. Now, how about here? Let's apply the root test. So here, once again, they call it rho for the root test. Take the limit as k goes to infinity. The kth root. Nothing is negative here. We don't need absolute values. So we're going to have 6 divided by k to the kth power. So we end up with the limit as k goes to infinity. The only thing that's left is the 6 over k, so that limit is 0. All right, now we're in the root test, so we're comparing to 1. This is less than 1, therefore
Converges.
convergence. So just like the ratio test, just like the geometric series, so those 3, root, ratio, geometric series, we compare to 1. Divergence test, we compare to 0. And so we have convergence here by the root test. So that one works out beautifully. Beautifully. Okay, now top one's a weird one. Top one is a weird one. In your mind, visualize the sine curve. So it's just wobbling around between -1 and 1. Right? So you have that in your mind, and now you think about these k values. These k values are in the denominator of the angle. So is the angle getting bigger or smaller? The angle is getting smaller. So now visualize the sine curve as the angle gets closer to 0. What is sine of 0?
1.
Sine of 0, if you go to the unit circle, you go to 0 degrees, 0 radians, sine is second. Sine is the second coordinate. Sine of 0 should be 0.
Yeah.
So, and you can visualize this in a couple of ways. If you can think of it like the graph, or you could think of unit circle even. So unit circle, if we start having an angle that's approaching 0, so we're going this direction, we've got this little angle here, and as we come down, the sine visually is this height right here, right? That little segment represents sine. And as the angle is going towards 0, that's going to 0, okay? So the limit of this is 0, so the divergence test is inconclusive. And so the question is, how fast do these converge? And the natural thing to do is to try to compare it to something. And there is a way that that I want you to think about this. If you are on a unit circle, is it clear to you that angle and arc are equal? If you're on a unit circle, is it clear that the angle and the arc have the same value? Okay, let's see. So if you're on a unit circle, so the radius is 1, right there. Here is the angle, I'll call it theta. Here is the arc over here, which I'm going to actually, let's use a different color for the arc. So there's the arc right there. So that arc is S. And we know that the formula says that theta is equal, there's a formula, can you tell me what the formula is for theta, R, and S?
Half of R.
The formula for, so if this was a general circle here and I just called that R, and R is going to be 1, but if you have theta, R, and S, what's the relationship?
R theta.
S equals R theta, correct. And if you're on a unit circle, you get S equals to theta when R is 1. All right, so the arc and the angle have the same magnitude. Okay, so this is a unit circle, so let's get rid of that so that we can see that it's a unit circle. Okay. Now, we just talked over here that the value of sine is right here. That vertical height right there, that is sine. As the angle is going to 0, you can kind of see that the angle and the arc are both approaching 0. Is that okay? All right, so let's think about one other perspective. If you look at the sine function's graph, if you look at the graph of sine, it looks like this. And the tangent line for sine is going to go right through the origin. When you get close to 0, whether you're looking at the unit circle or you're looking at the graph, sine of x is approximately x when you're close to the origin. So here, as this angle gets closer and closer, that arc and that vertical line, they look like they're the same height. Sine of theta and theta are about the same. Here, when you're coming closer and closer to the origin, there is y equals x, there's y equals sine x. They become indistinguishable as you get closer and closer to the origin. In other words, this is the trig function sine. This is the angle. We're going to compare it to the angle because sine of x and x are about the same when you're near 0. So what we're going to compare this to, we're going to choose our b sub k to be 1 over k to the 9. And does this series converge or diverge and why?
Converge because P equals 9.
So p is 9, which is bigger than 1, therefore converge. So our hunch is that this series converges. So if we do a comparison, we would want to show that a sub k is less than b sub k because we have a convergent series. Smaller than converging converges. We look at our a sub k is the original, so sine of 1 over k to the 9. And the question is that less than 1 over k to the 9? And when we look at our picture right here, sine is this vertical purple distance. S and the angle are the same. And which is bigger? Is S bigger than sine? Yes. Right? Sine is this vertical purple distance. Green is S, which is the same thing as the angle. And sine of theta is always less than theta. You can see it from this picture. In Calc 1, you would prove it by taking a derivative and doing some things with derivatives. This is true. Therefore, both are going to converge because that is true. So you can think of sine of x is about equal to x, and we're going to actually see this again in the next chapter, when you're close to the origin. So sine of some angle is about the same as the angle. And so if we look at this picture here, we can see that, okay, well, the angle and the arc are the same, and sine is that vertical distance right there, that purple vertical distance. That's always less than s as you're going down to 0. That arc is always a little bit more because there's some bend to it. So the arc is bigger than sine. Therefore, they both converge. All right, last one, and then we get to go to chapter 11. We get to power series. Every engineer's favorite subject. We see a power on the outside here. So our instinct is to use the power on the outside. We're going to use the root test. Power on the outside. When we take the kth root of this, we end up with one of those k's vanishing. We take the kth root of k squared, one of the k's goes away. So we took the kth root of this, we get that. All right, this is a limit. Actually looks a lot like one we just did with the e. So this is going to be the limit of, let's flip the base. And if we flip the base, we toggle the exponent sign. We can split the fraction now that we have flipped the base. We now have a limit that we can evaluate with this general formula,
E to the 10.
e to the 10. All right, now we have to remember how to do our analysis. Root, ratio, and geometric, we compare to 1. This is root. So root, ratio, geometric, we compare to 1. Divergence test, we compare to 0. Is this bigger than 1?
Yes.
Therefore,
Divergence.
diverge. So root, ratio, and geometric, bigger than 1, diverge. All right. Here we go. Power series. Unless someone has a question on this. Okay. So, the most important piece of calculus 2, power series. First question, what do we mean by the term power series? Well, we just got finished dealing with infinite series, which in calculus, if we say series, we mean infinite series. So this is an infinite series of powers. So now we're dealing with an infinite series of powers of x. That is what we mean when we say a power series. When you hear the expression power series, you should be thinking of a polynomial that has increasing powers forever. So this is a lot of times when we write our polynomials, we like to write them in descending powers, x squared plus x plus 1. Power series, we do the exact opposite because the powers never end. It's a power series. So we have the constant, and then the linear term, and then the quadratic term, and then the cubic term, blah, 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 forever. So a power series is an infinite polynomial. It's a polynomial, I mean, using the term polynomial in quotes, because a polynomial has a power, right? It has a leading term, leading coefficient, leading highest exponent. But this has no highest exponent, it goes forever. But it's a never-ending polynomial. This power series is centered at 0. This power series is centered at A. So you've done this in algebra. If you have y equals x squared, that parabola is centered at the origin. If you have y equals x minus 2 quantity squared, you shifted it 2 units to the right and it's centered at 2. That's how we're going to think of these power series. If there's nothing added or subtracted to the x, it's centered at the origin. If something is added or subtracted, whatever comes after the minus sign is considered the center. So if it was x plus 3, the center would be negative 3. Just like when you graph y equals x plus 3 quantity squared, it shifts it to the left 3 units. So the center is considered negative 3. So this is what we mean by power series. Infinite series of powers. Now, these are functions. The series that we looked at in chapter 10 were not functions, they're numbers. Right? You added up a geometric series and you got a number. It was just a nasty way to write a number. Right? If you added an infinite series together and it converged, you just got a single number. It's just a number. When you think about these power series, you can plug in any x you want. You can plug in -5, you can plug in 0, you can plug in 1, you can plug in 2, you can plug in pi, you can plug in whatever you want, I. You can plug in any number you want. Some of those x's that you plug in will generate series of numbers that converge. Some of the x's you plug in may create series of numbers that diverge. So our sense of domain is now going to change. Normally when we think of domain, we think of the x's for which the function is defined. So if you have the square root of x, the domain is 0 to infinity because square root is only defined from 0 to infinity. For a power series, the domain will be the set of x's that give you convergent series. The numbers that give you divergent series will not be in the domain. So the domain, the concept of domain is now different. Any x that we plug in that generates a convergent series, that's going to be in the domain. Any number that causes divergence is not in the domain. All right, so keep that on the back burner. Here are 2 examples. The most important example in math and engineering is the power series for the exponential function. That is the power series for the exponential function. This is the expanded form of it. This is the summation notation or the closed form for it. The interval of convergence, domain. The domain is now going to be called the interval of convergence. The interval of convergence for this power series is all real numbers. You plug any real number in for this x, 10 million, 5, 12, -5. You plug any number in there and you will have a convergent series of numbers. So for example, if you were curious about how to write e squared as an infinite series of numbers, just because you were curious, all you do is plug in a 2 right there. E squared, you just replace all these x's with a 2, and this infinite series of numbers will, in fact, add up to e squared. If you want just e to the 1, just replace all those x's with 1. And you will have an infinite series of numbers that adds to that value. If you want the square root of e, what are you going to replace the x with? 1/2. If you turn all those x's into halves, that will be an infinite series that represents e to the 1/2 or the square root of e. That's how our calculator does it. Calculator, for the calculator to compute a sine or a cosine or an e to a value or a log of value, it's going to use this infinite series, and it's going to go out far enough, as far as it needs to get the accuracy that your device requires. Here's another power series. This power series is centered at 1, not 0. This one is centered at 0. There's not an x minus or an x plus anything, so it's centered at 0. This one is centered at 1 because we have x minus 1 in all those power positions. So that one's centered at 1. This one had a domain or an interval of convergence that was very big. The whole real line. Didn't matter. This series only makes sense on this interval. Open at 0, open at 2. So 0 to 2. Any other number, so if you plug in 0, you plug in 2, or you plug in bigger than 2 or less than 0, you'll get divergence. The only x's that will give you convergence here are the x's between 0 and 2. So this series has a very limited interval of convergence. Now, I'm calling them intervals of convergence. So we are going to see the following phenomenon. Notice that the 1 is dead center of the 0 and the 2. We are going to see that whatever the center is, you will generate convergence in a symmetric interval around that center point. You will never have an offset interval. You'll never have the center be at 1 and the convergence be at, say, 0 and 5. It's always going to be an interval of convergence. All right, centered at the center. All right, so we will see that. The next step in getting a handle on these power series is to go back to Calc 1. So now in our mind, we've got these infinite polynomials. We're going to start from the beginning. So when we looked at those infinite polynomials, like we look at e, it was 1 plus x squared over 2 plus x cubed over 3. And I just mentioned that sometimes you only go out a certain distance. How do we get these terms? How do we create that power series for e to the x? How do we get to this 1 plus x squared over 2 plus x squared over 3 factorial, or x cubed over 3 factorial? How do we get there? We go back to the beginning. So we go back to Calc 1. We have this curve, y equals f of x. In Calc 1, you learned that the best linear approximation to that curve is the tangent line. Right? That's what you learned. The tangent line had this equation. You did this stuff, you found the slope of this line. The slope of that line is f prime of a. And if you wanted to build the equation of that tangent line, you did the point slope formula, and you ended up with this function. In Calc 1, you usually just called it y. We are going to call it P1. So P1 is the linear approximation. It is the tangent line's equation. Point slope formula gives you that equation. Notice two important features about this tangent line. So here, this says that the tangent line's value at a matches the function's value at a. So in other words, f of a and p1 of a are the same. Duh. It's a tangent line at a point. They have to match at that point. The value of the function and the value of the tangent line at the point of tangency, they have to be equal, right? That's how, it's a duh because, yeah, that's how we created it. We drew that tangent line so that the value of the function and the tangent line match. And then the more important property that you learned in Calc 1 was that, oh, they also have the same first derivative value. Right? So the slope of the tangent line is the slope of the curve. They have the same derivative. So the derivative of the tangent line and the derivative of the function match. Right? You found, and the way you built the tangent line was to take the derivative of the function, you plug in your a value, you get that number. That's the coefficient of x for the tangent line. So now we're gonna, that's pretty minimal. We just took one derivative. You learned in Calc 1 that you can take a bazillion derivatives. These are going to lead to the subsequent terms in the power series. So, we are going to now, the best linear approximation, that just seems so basic. Now we're going to look at the best quadratic approximation. And you can just see already, the blue is the best quadratic approximation. You can see that it matches the function in a much wider interval. The tangent line is only a good approximation if you are very short-sighted. You've got to be right near that point of tangency. As soon as you move away from the point of tangency, the tangent line is crap in terms of approximations. And if you move over to here, there's the tangent line value and there's the function value, right? Terrible! The linear approximation is only good when you have a very narrow field of vision. Only when you're very close to A. It's the only time it's good. Not useful. Now you look at this quadratic approximation. This quadratic approximation is good on a much wider interval. Right out of the gate, the second derivative is giving us, or the second order approximation, the quadratic approximation, is giving us a much better match to that function. And you can see where this is going. If you get the best cubic approximation, or the best quartic approximation, the degree of closeness spreads rapidly. And that's what a power series is. It's an extension of the best approximation. So when you look at this power series that we had for E, when you look at this is the tangent line right there. That's the best linear approximation for E. That is the tangent line. This is the best quadratic approximation. This is the best cubic approximation. So we are extending the idea of the tangent line in a very dramatic way. Instead of one derivative, we're going to do all derivatives. And we are going to build a power series that matches the function exactly everywhere in the interval of convergence. And that's exactly what our computing devices need in order to be useful to us. So how do we, so we're going to bootstrap our way through. There's going to be a bunch of patterns, of course. We're going to start by saying, okay, well, we know how to create the tangent line. Now let's build the quadratic approximation, and let's see if there is an extension to all derivatives that we can use. And of course there's going to be. First off, here is our tangent line right there. So the tangent line, this is what you learned in Calc 1. When you build the tangent line and you isolate y, that's it. That's what it looks like. What we're going to do is add a quadratic term to that. So we're going to say, okay, we've got this line, it's a tangent line, now let's add a quadratic term. And we need some things to happen here. When we built the tangent line, we needed two things. We needed value and slope to match. The tangent line is the best linear approximation because the value matches and the slope matches. When we build this quadratic approximation, we want the value to match, we want the slope to match, and we want the concavity to match. So we want the 0th derivative, the value, the first derivative, the slope, the second derivative, the concavity, all to match. So when we build this polynomial, we're requiring value, slope, and concavity all have to match. So we need the value, the slope, and the concavity. That's what we're going to mean by the best quadratic approximation. The best quadratic approximation is going to be the one that has value, slope, and concavity all matching the function. And there's only going to be one of them. We will see. So, now we have our quadratic. There's a constant term, there's our linear term, there's our quadratic term. Ooh. So look at this. Let's confirm that the values match. So the tangent point is A. That's the x value. So if we plug in an A right here and right here, so P2 of A, if we plug in A there and there, this term disappears and this term disappears, and we have the value of the function is going to match the value of this quadratic approximation. Right? If you plug in A, both of those disappear. So this shows us that the value matches. Now let's find the derivative of this second order polynomial that we are constructing. So let's take the derivative of this. What is the derivative of f of A? F of A is a constant, so its derivative is 0. Right? F of A is a constant. The variable is x. Right? There's the variable. So when we take the derivative here, the derivative of this term is 0. F of A is a constant. That's 0. Now we want to take the derivative of this term right here. Okay, the derivative of this, f prime of A is a constant. Right? F prime of A is the slope. It's a constant. So this piece right here, if we look at f prime of A times x minus A, if we distribute this f prime of A, which is just a constant, so we get that. F prime of A and A are constants, so what's the derivative of this part? 0. This is linear. What's the derivative of this whole term right here? F prime of A. It's the number in front of x. If you have 5x, the derivative is 5. If you have 10x, the derivative is 10. If you have random constant times x, the derivative is random constant. So that's what this is. Right? This is the derivative of this middle term. Now let's take the derivative of this last term. Okay, power rule. Bring down the 2 in front. Subtract 1 from the exponent. Chain rule, multiply by the derivative of the inside, which is just 1. So the 2 comes down. That is now the derivative, right? So this is the first derivative of our second order polynomial right there. Now let's test. Does slope match? Right? P prime is the slope of this approximation. All right, there's the slope. If we plug in the point of tangency, if we plug in x equals A, this term disappears when we plug in x equals A. So those will be equal. The first derivative of P2 and the first derivative of the function match. So now we've shown that we've got value matching. Now we've shown that we have slope matching. Let's take the next derivative. Second derivative, doink, over here. Oh, derivative of a constant is 0. Derivative of f prime of A is 0. It's just a constant. Now we look in here, we want the derivative of that. Same idea that we did over here. If you distribute the 2c2, so the c2 is just a constant. So isn't the derivative of this just 2c2? Right? This constant gets distributed to the x. This constant gets distributed to the constant. The derivative of that constant is 0. The derivative of 2c2 times x is 2c2. 2c2. So we end up with this right here. And we are saying that the second derivative of the approximation must match the second derivative of the function. So if we divide both sides by 2, we get this. And that has to match the second derivative of the function. So this and the function second derivative have to be equal. That is what the second constant needs to be. This C2 constant needs to be f double prime divided by 2. Just like this first constant needed to be f single prime divided by 1. So now we have a pattern to generate these constants. or we've at least started to see what the pattern is. If we were going to go to the third order approximation, what might you suspect? Let's put it in green. What might you suspect? We're going to have an x minus a cubed so that the value, the slope, the second derivative all match, value, slope, and concavity. What do you think this constant's going to be?
F triple prime A over 3.
So our first guess is going to be f triple prime a over 3. And that is almost it. There's one caveat. If you do this, you're actually going to end up with a 6 here instead of a 3. And we are going to see that this is really a factorial in the bottom, not just the power, not just the order of the derivative. So you're going to see if you were to if you're going to do a couple, if you were to do the third and fourth, you'd see, oh gosh, okay, it's 3 factorial and then 4 factorial. So that is going to be our pattern. So let's play with the second order stuff before we extend it to forever. So let's think about first and second order approximations and just get a handle on those, and then we'll talk about these extensions. So they give us a function, and they give us a center. And they want us to build the linear and quadratic approximations. So in building these, it's going to be helpful to be very systematic, and I usually create like a table type of thing. So we're going to start with the function. And I'm going to use y's instead of f's. It's just a little bit less messy. So here is the function. Now the derivative of the function. Now the second derivative of the function. Okay, so take the function. To create the second order approximation, we need the second derivative. To create the first order approximation, aka the tangent line, we need the first derivative. Now, second column. First let's rewrite these without negative exponents, just because a lot of times it's useful to have no negative exponents. So let's do this. Okay. So we've written them all out. Now, what we have to do next is evaluate all of these at our center. So we've seen that the value at the center, the derivative at the center, in other words, the slope, and the concavity at the center. So if we think about, maybe I should write that whole general formula or polynomial over here. So P2 of x, we want to write that whole thing out. That was f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a squared. So that's what we concluded was the second order approximation. So the first part's the tangent line, and now we've added the second order term, this term that's going to give us the best quadratic approximation. So we see that we have to evaluate the function, the derivative, and the second derivative at A. A is the center. They tell us, build this approximation around 1. So if you want to visualize this in your mind, we're thinking of this function, 1 over x, looks like that. And we're looking, our focus is right here. So there's where 1 is. So there is the point of tangency. We know that that's going to be the best linear approximation right there. And now we're going to find the best quadratic approximation. So let's see. Well, we're going to find both. So next step in the process, evaluate f prime, f double prime at A. So second column in this imaginary table. So I'm going to say, let's find the function at A. Let's find the derivative at A. Let's find the second derivative at A. Okay. Well, the function at A, we plug in a 1 and we get a 1. First derivative at 1, we get negative 1. Second derivative at 1, we get 2. So those are our constants. Function, derivative, second derivative. So if we come over here to build p sub 1, that's the green one, that's going to be f of a, right there, function at the center, plus f prime of a, negative 1, multiplied by x minus 1, because a is 1. So this is P1. We can simplify this. If we distribute here, we're going to get 1 plus 1 is 2, so we're going to get 2 minus x. Now, as we start to go on in this business here, we rarely are going to actually do this simplification because the simplification kind of obscures the patterns. So we're usually not going to simplify, but with these simpler ones, it's helpful. That's this equation right here. That's this function. This function is y equals 2 minus x. That is the best linear approximation to 1 over x. That is the tangent line. Now we're going to build p sub 2. So p sub 2, we're going to start with this whole thing. And then plus the second derivative divided by 2 times the center quantity squared. And again, normally we're just going to leave it like this, but if we wanted to, we could simplify this by squaring everything out and getting like terms. Maybe we'll do it this time, but we're not going to do this in the future. So 2 minus x is this first part, and then that's a 1. And then here, if we squared it out, we would get x squared minus 2x plus 1. So let's see. So we would write this as 3 minus 3x plus x squared. So that is going to be the best quadratic approximation to 1 over x. Now, how would we put this in fact, you know, what do they call it? The vertex form or whatever they call it these days? We used to call it just standard form. You know, the a times x minus h quantity squared plus k, the standard form. A lot of times they call it vertex form now. If you were to put it in that form, you would first write it in descending order. And you would do a complete, you would get the vertex by negative b over 2a, blah, blah, blah. So you could find the standard form of that.
Maybe plus 3 instead of plus 2.
Oh, yeah, plus 3. Thank you. So what is the vertex here? The vertex is negative b over 2a. And then to get the y-coordinate of the vertex, you plug it in doing this thing. So the vertex would be negative b would be 3 over 2. And then if you plug 3 over 2 in here, you're going to get 9/4 minus 9 halves, which is minus 9/4 plus 3 minus 9/4 plus 12/4 is 3/4. So the center of that parabola is going to be over here somewhere. 3/4 is less than 1. It's going to be somewhere like that. And it's going to be, you know, coming, it's going to touch that point and then go up, something like that. But it's got to touch right here. It's got to have the same value. So it's going to be something like that. And so that quadratic is going to have a much wider interval where it's matching the function. Now, normally we're not going to like rewrite this. We usually want to just keep it in these two general forms because you can see the pattern, and simplifying is not going to give us that much value. So let's answer the question about the approximation. So this said we want to approximate 1 over 1.05. So 1 over 1.05, if we look over here, 1.05 is, you know, like right in there. So 1.05 is somewhere in there. So let's do 3 things. Let's figure out f of 1.0, because we can do this. With these first ones, there's no need to approximate here because we can just type that into our calculator and get the value, like we know it. But we always start with things that you could do in other ways. So let's figure out that. And then let's figure out P1 of 1.05. So we're going to get all of these approximations, these two approximations in conjunction. So let's look at this first, P1 of 1.05. So come up to P1. So you could go to either of these places, doesn't really matter. So we're going to subtract, if we go here, we're going to subtract off 1.05. So if we subtract 1.05 from 1, we get 0.95. So that's our approximation. If we go to P sub 2, plugging it in there is going to be kind of a pain. It's actually going to be easier to plug it in right there. So we're going to end up with 1 minus, if we plug in 1.05 here, we're going to end up with 0.05 there. And then here, that cancels. Plug there, we get 0.05 squared. So whatever that all adds up to. If we do, I might need somebody to do this on their calculator and do it in Desmos or something, just so we can sort of see. Desmos is always a convenient little thing to have open on the side if you're doing approximations. Let's see. Oh no, Prim's right there. .9525. 0.9525? So I'll do them all right here, then we can just copy them over. So 1 divided by, what was it, 1.05? 1.05 is that. And then we have the 0.95, put it there. And then we have 1 minus 0.05 plus 0.05 squared. So those are our three things. And if you look at and compare, you can see how the approximations get better. So when we look at that situation, let's get you out of the way a little bit. When we look here, so here is the actual value, right? That is the true value. This is the first approximation, which is good to the second decimal place. And then we go to the second approximation, the second order approximation, and it is good the first 3 decimals it's already matching. So that's the idea, is that the further out in the series, well, the further out, the bigger the polynomial, the further out in the series we go, the better the approximation is going to be. So that is the general gist of it. That if we keep going out, create the best quadratic, then the best cubic, then the best quartic, etc., we will get better and better approximations. And as we go further out, we'll see that we can get as much accuracy as we want. So let's try one more of these. So looking at this function, let's do the same exact thing. So we start with our function. I'm going to use y's instead of f's. It's just a little less writing. We need to go down to the second derivative. So first off, we're going to just do our regular derivative stuff. And I'm going to write these with negative exponents right from the start, just so that we can not have to deal. Okay, so do you agree with those? I don't. What is this power here?
Negative 3 halves.
Negative 3 halves. I subtracted 1 incorrectly. So that should be 3 halves here. I think I agree now. So 1/2 down, subtract 1. Negative 1/2 down gives us negative 1/4. Subtract 1, we get negative 3 halves. Okay, next we evaluate. So they tell us that our center is 4. So we want y of 4, which is 2. Y y prime of 4, which is 1/4, y double prime of 4, plug in the 4 there, square root of 4 is 2, 2 cubed is 8, 8 times 4 is 32, so we get negative 1 over 32. So now we have all our constants. Now we can build our approximations. So our approximations, P1 of x is f of a plus f prime of a times, bless you, x minus a. There is our tangent line. And we're going to leave it like that. We're not going to expand it anymore. So that is our tangent line. P sub 2 of x is the tangent line, so this all stays the same, plus y double prime divided by 2. So minus 1 over 32 divided by 2 times x minus 4 quantity squared. That is our best quadratic approximation. Now we can evaluate these things. So we want to approximate the square root of 3.9. So x, if you match, there's x. So x is inside the square root. So what's in the square root is x. So that's going to be what we replace the x with, 3.9. So P1 of 3.9 and P2 of 3.9. These are our approximations. So 3.9 goes in here. 3.9 minus 4, negative 1/10. So we're going to have 2 plus 1/4 times negative 1/10. And then down here, we're going to have that same thing. And this is going to be negative 1 over 64, negative 1/10, quantity squared. And we are going to get approximations for each of those. So, pull up our grapher. And figure out. Let me get the bottom. There we go. So our first approximation is going to be, just going to add this stuff up. Well, I guess that's really minus 1 over 40. And then 1.975 minus 1 over 64, parentheses. I guess that's 100th. So there are the approximations. And we can get that original value also. What was it, square root of 3.9?
Yep.
So there are our 3. Hopefully.
The second one's already good to the 5 digits after the.
It doesn't take much. Yeah, so that second order approximation is already really darn accurate. So this is the original approximation. So this one goes out to 2 decimal places, and this one goes out to
5.
1, 9, yeah, oh my gosh, yeah, way out there. 484, yeah. So they usually, if you have the right series, it converges quite fast. Quite fast. And you can imagine a calculator. A calculator can do these computations, adding, subtracting, multiplying powers really easily. And so that's what the calculator is going to do. Okay, so let's take a look at a generalization. So our generalization is called, instead of the best linear approximation, the best quadratic approximation, we just call these Taylor polynomials. So the first order Taylor polynomial is the tangent line. The second order Taylor polynomial is the best quadratic approximation. The third order Taylor polynomial is the best cubic approximation, etc. And this is what a Taylor polynomial looks like. It's just S sub n. It's just the sum of the first n terms of the series. So a Taylor polynomial is the leading terms of the infinite series that we're building towards. So the nth order Taylor polynomial has n plus, I should have actually called it S sub n plus 1. Because aren't there n plus 1 terms here? If this goes to power n, this is power 1, this is power 0. So it's actually S sub n plus 1 if we're thinking about what we did in chapter 10. And the generalization of the coefficients is right here. The coefficients, we just did the second derivative over 2 factorial. If you go to the third derivative, it's going to be over 6. It's going to be over 3 factorial. Here's some pictures. So e to the x is that function right there, the black curve. The best linear approximation is the red. The best quadratic approximation is the blue. The best cubic approximation is the green. And you can see it. You know, the further out you go, the better the approximation gets. And there's some really cool animations in, I can't remember if I logged into Desmos. Is it going to remember? I doubt this is going to work. Yeah, I'm not going to deal with it. I'll log in next time and show you some good visuals. Actually, we might be able to just see if we go here to examples. Is there any Taylor tell me if you see the word Taylor polynomial anywhere.
Yeah, I do.
Where?
Well, it's down.
Down?
Taylor expansion of.
Yeah, where is that?
Down, one,
Down.
right there.
Here, oh, okay. All right, so here's what it's going to look like. So let's, okay, this is the center. The center, that does not look like the center. No, the A is not the center. Okay, this is centered at 0. You can see the center at 0. They used an A here to represent the power. So we're dealing with the function sine. So sine is in red. And the best approximations are going to get better and better. Their A is not matching the power exactly. We'll talk about this later. But you can see that as you go further and further out in the series, the interval of convergence, the interval that gives us the best accuracy, gets better and better as you go further out in the series. So that's what a Taylor series does. That's what these infinite series do. They just start to wrap. If they converge for all reals, they just wrap around the function exactly. Now, one question that you might ask is, well, why would we center a Taylor polynomial or a Taylor series, we're going to call them, anywhere other than the origin? And so you can see here that if we were trying to approximate sine, say over here, sine of 7 or 8 radians, for this series centered at the origin, we would have to go pretty far out. So notice that when this A value is 10, so when A is 10, so n goes from 0 to 10, if we plug in a 10 there, the power here is 21. Whereas if we centered this, say at that 0 right there, which we could find, then you'll only have to go out a tiny bit from that center. So the idea of moving the center, you move the center near where you're trying to do your approximation. And if you get your center as close as possible, you need to go out as little as possible into the series. All right, let's go ahead and pause for Halloween. Scary Power series. So I highly recommend doing a bunch of work with these over the weekend because they get hard fast. So Get caught up this weekend, get all your chapter 10 homework done.
I was feeling so good about this next test, chapter 10.
I know.
I don't like this.
Chapter 11
No, this will be.
throws a little monkey wrench into it. But it's cool. It's tough. And I will get logged into that.
We have shifts like
Week.
morning and morning.
Have a great weekend. Boo.
Where are you going as for Halloween?
I'm going to my son's house for dinner, which is going to be, I'm sure, weird. College kids and dinner on Halloween. What's going to happen? Who's going to drink the jungle juice?